Good morning and thank you for joining us. Today we're going to be talking with you about intelligent latency aware and load shedding service routing. I'm Jason Griggs. I'm part of the platform performance team, and I'm joined with Huajun, who is part of middle office platforms. And we work for wealth management technology at Morgan Stanley. Today I'll be talking with you about Ticketmaster, load shedding, and the Taylor Swift incident from last November. We'll be talking about how Morgan Stanley is able to creatively solve database latency by utilizing an in-house service that we created called Beacon. And I'll be talking with you about how Beacon architecture has been improved over time. And last, I'll be going over metrics in production from Beacon. Have you ever tried to purchase tickets to a popular band before, and only to get stuck in queues for hours, or you end up not getting the tickets that you wanted? Or you ended up having the website, it was totally unreachable, you're trying to load it. Well, that perfect storm happened in November of last year, when Taylor Swift had her pre-sale for her upcoming concert tour. There were three key areas that Ticketmaster had their site hammered by. They had fans with pre-sale ticket codes that was legitimate. They were there to be able to purchase tickets. You had fans that didn't have pre-sale ticket codes who were trying to guess as far as what the ticket code could be so they could get in and get tickets to a concert. And you had bots that were going and hammering the site trying to go and get in there and be able to purchase tickets.
Bots love Taylor too.
So, I was not one of those fans that was trying to get tickets, but maybe some of you were. And as a result, you had fans that were in the ticket queues for many hours. And the way that Ticketmaster wanted to be able to handle this was to be able to have the pre-sales go across subsequent time zones in order to handle that load. What they didn't plan for was this perfect storm that occurred. So when the East Coast pre-sale started, you ended up having fans that ended up being stuck in queues for many hours. And as a result, as the subsequent rolling over to the other pre-sales in the time zones occurred, when it ended up being that time for the West Coast pre-sale to start, you still had fans that were in ticket queues from earlier that morning. And this threw off the schedule completely for them. They just did not anticipate this. But what I will say is that in the end, Ticketmaster was able to complete more than 2 million plus ticket sales for this pre-sale for the concert tour. Now, there are other areas where we have sites that have similar challenges today. We have online brokerage firms with market swings, and some of you might be aware of some of the things going on in the news. And that can cause a lot of people to log on to their brokerage platforms wanting to be able to trade stocks and be able to do things on there. And then we have social media sites with sensational news, and in this case, when it comes to what's been going on in the markets, those two are kind of closely linked. So you have people who are logging on and wanting to see what news is trending, what's going on, and what people are talking about. And then you have retail sites when there's holiday sales, such as Black Friday, Christmas, Labor Day, Memorial Day, President's Day. And depending on the sale, you can have a lot of people that are going to that website to try and make purchases. And you want to be able to handle that load. And there are many others that I could go over and talk about, but this is just to name a few. Now, different companies have honed in on special architectures and operational tools to meet their needs. We have event-driven architecture, microservices architecture, SQL database and replication and partitioning, NoSQL and distributed SQL. This presentation, though, will focus on database replication for load distribution. In large financial service systems where a system of records are kept in relational databases, database replication and vertical partitioning are commonly used to provide read-only copies for resilience and performance. Most data queries, though, are directed to the replicas to relieve the load from the primary database servers. In a microservices infrastructure, data is accessed through services. Online service can make multiple and nested calls to other services that access multiple replicated databases with fluctuating replication delays. Infrastructure support, though, is required to manage and monitor the data services to provide quality of service to the customer. So imagine that you want to return data back to your customers to offload the traffic to the primary database. You're going to go to the read-only databases. But you have various levels of freshness of data that you could be returning. You could return the data that is replicated as is to the customer. You could provide the data with an as-of timestamp to them. Or you could route the query to the primary database, but doing that only if the replication delay exceeds a preset threshold based on the read-write versus the read-only database latency. So how do you go about ensuring that the current information is being returned to your customer while guaranteeing quality of service to them? You could route all the traffic to the primary database when a latency threshold is exceeded, but that can cause excessive load on the server. Can we do better? A key observation we have is that not all customers have the same level of updates to their data. Customer activities and replication delays are fluid. So how do you decide where to route the data queries to ensure quality of service? With these challenges, Beacon came into existence, and this is how we solved that. And the way that we achieve this for our customers is with intelligent routing of services to either read-only replicas or primary data servers. So Beacon consists of three main components. We have a Beacon router, we have a Beacon status server, and we have a replication latency server. Now, to go in a little bit deeper while still trying to stay high level, imagine with me, if you will, that you go and you place an order on one of our trading applications in the stock market, and that order is executed. And you want to go and see that that order has been executed. Well, you go and you send a request through an application that we have, our platform that is. That goes and is taken in by the Beacon router server. And the Beacon router server, it extracts the key from the request. It sends the key to the Beacon status server. And what the Beacon status server does is it goes and checks the latency from the replication latency server. Now, what the replication latency server is doing is keeping track of the latencies between the primary and the replicated databases. And it turns that information back to the Beacon status server when the last activity is of the key, and that is sent back to the Beacon router server as to whether or not that key has been replicated. Now, the Beacon router server will make a routing decision depending on the Beacon status that's been received. And it will direct it to the read-write service or the read-only service, depending on the latency. Now, to go over our Beacon 1.0 architecture, I'll pass this off to Huajun.
Thanks, Jason. Yeah, let's walk through the Beacon 1.0 architecture diagram to see how we beaconize a service. So here, the service actually we describe. We just put a name, just call the service X. Right? The service X was previously configured to talk to primary database to get data back. So how we can beaconize this service that it will be able to shred the node from the primary database to the replica. So with the concept of beacon, what we do actually in our service infrastructure, we can allow a service to take over a service name and be in front of the original service. So what this does is when a client sends a service request, the beacon router would intercept the request. The beacon router is a service that can be configured for any other services. So what it does actually, it tracks the payload from the service and use XPath to find the key that the key can be used to make intelligent decision where to route the data to. So for example here, then the beacon router extracts a key 1001, and it will then send the beacon key to the beacon status server. Now, beacon status server actually makes two calls. One is to make a call to the rep latency server that checks what is the latency for a configured service. So as a part of the router is also configured with a name called module. The module is really kind of closely related to which type of database it talks to. So from here, the rep latency server gets the latency back and then send it back to the beacon status server. Now, beacon status server will make another call to a beacon DB that tracks the last update activity for that key. So this is actually pretty unique in our infrastructure because we have massive vertical partitioning of the databases. And we have to use compensating transactions to actually keep integrity of the transactions. So when a transaction is being made, actually it will have application level knock-in. And from that knock-in, we will be able to turn that, create a material view, and be used by the beacon to find what's the last update time for that key. For example, if an order is placed for an account, and then the order execution would actually send the popular data back into multiple databases. But all the database tables being updated would have the same account key. So with the application level knock-in being part of infrastructure, we will know exactly what is the last update time that happened for that key. So for here, when we get the last updated key, updated time, and also we compare the latency between the primary and the replica, we will know for sure that the data has been replicated to the replica for that key or not. So if it's indeed being replicated properly, then the beacon server will return in sync back to the beacon router. For the status in sync, it actually will forward the service to a service XRO. So in case actually the replication has not caught up, it will be routed to the service XRW. Now in our infrastructure, it's not just regular RPC type of style, so we also can truly support service forwarding. So essentially, when the service XRO or XRW handle the request, they will be able to send the data directly to the calling client. I'll give this back to you, Jason.
Thank you, Huajun. So when Beacon was originally architected, we did have some operational burdens that came with it. We were periodically sampling one database per module to determine our latency. And originally, when this was built, there were very few databases. But this led to one database latency being used for all database latencies. And latency had to be more closely monitored as a result. What this did is it burdened the operations team to have to manually override to the primary database when there was a replicant issue. In doing so, this threw all the traffic to the primary read-write database for a manual override due to a single database replicant issue, even though the other replicant copies were current. We replicate our databases not only for performance, but also for resilience. we have separate domains of databases for customer service and for active traders. So in other words, when an active trader is directed to one of the database replicants, they're accessing replicants specific to active trader. And the same goes when accessing replicants for customer service as well. So we got on our thinking caps and we thought, what can we do to take this service and take it a step further beyond what we currently have? We have resilience, we have performance and quality of service, but how can we take and raise the bar on this without having to sacrifice any one of these other areas? And with that, Beacon 2.0 was created. Now, one of the terms that I'm going to use here, and I did reference it in the previous slide, 2 slides ago, was domain. And what that refers to is a logical group of replicated databases. Now, as we handle our customer traffic, we channelize the replicated data to domains on specific platforms, such as website, mobile, active trader client, and we do this for installation from each other. Now, if you remember when Huajun was going over the Beacon 1.0 architecture, he touched on the replication latency table. Now, the thing we did in Beacon 2.0 is that we actually replaced that table. And in replacing it, we replaced it with a replication latency domain table. And what this does now is it allows us to keep track of the replication latency for each domain database. Now, each domain database will know the latency for its own data server. And this allows Beacon to now operate independent of the other domain databases. So when you have one slow database replicant, it'll no longer affect the routing on the other domain databases. Oh, in our Beacon 2.0 architecture here, I'll pass it off to Huajun.
Yeah, thanks, Jason. So let's take a look of how Beacon works under Beacon 2.0 architecture. So my client sends out a request. The Beacon router would work just as before. There's no change actually in the Beacon router. It still extracts the key using XPath, and then sends the request down to the Beacon status server. Now, as a part of the architecture 2.0, we enhanced the Beacon status server to take the metadata of which domain this service is being deployed to. So for example, here, if the Beacon status server is deployed for the module like balance, in domain 5, then domain 5, the balance and the domain 5 was sent to updated replication server. Now, replication server would actually take the balance and the domain 5 to get the information to replicating the data for that module and the domain. Now, before we go back to the return path, let's take a look of how all the green boxes that represent a subsystem that actually updating the replicancies for each domain. So here, instead of doing sampling of the replicancies for particular databases, for each replica database, we have background jobs that actually continuously monitoring the replication latency and then update the data back into replicancy domain table. We also have admin clients that actually can do manual switch over of a module and domain, either to override to primary database in case that database for that domain is behind, or also we suppose we want to do maintenance. So all this can be handled by the operations team. They can manually override per domain rather than switch everything back to the primary database. So let's kind of look the return path back. So here, the rep latency will be sent back to the beacon status server. That I was still taking the same step to look into the last update time for that key. Because this is a kind of condition for that domain, then for different domains, actually the latency might be different. And based on the decision, the calculation either the call is actually in sync or not in sync will be different too. Right? This actually has the advantage where one domain is late will not affect the routing of other domains. Like for example, we are talking about where we have a balance and domain 5, we get representative data back and compare with the last update time for that key. So if we decide in sync as before, it will get routed over to the XRO service. And if it's out of sync, it will be routed to the XRW service. And then the data, the response will be returned back to the client directly from the XRW or XRO. Right? Okay, give back to you.
As a configuration.
Oh, sorry. Yeah, I forgot to part of the explanation about beacon service as an infrastructure service. Right? So essentially, we can take a look of any service that you want to beaconize, and through the configuration of the beacon router, and we can just make that to be beaconized. So let's take a look of the beacon configuration here. So for this one, so we kind of, the original name of the service X, right? Then the beacon router will take this over and also specify that it actually the RO service and RW service is called X_RO and X_RW. So in case any of these kind of subsystem fail, we would route the service to the XRO. So this is supported that similar kind to electric grids, right? Like brownouts, or where you don't want to give just kind of outage out to the calling customers. So this actually will still be able to return potentially slightly data out of date, right? But that's really for extreme cases where the subsystems fail. And for this one, we have the XPath to track the value from the account key element from your X payload. And for example, here, the key could be 1001, right? It will be tracked from these XML IDs. Each actually beacon server can also be configured as a different service. So this will be X beacon status, and the module name could be balanced, right? So this one, for example, can be configured for the account, but you can define a different type of beacon status server for your user ID-based routing as well. So we have done that in our system in the past. Okay, hand back to you, Jesse.
Thank you, Huajun. So to recap here, we've talked about how beacon is configuration driven, as Huajun had just gone over. We've talked about how we're able to guarantee our quality of service to our customers, and how we're able to take database load shedding and be able to do it in a way that is performance and resilience driven. We've been able to take beacon and we've applied it to many services and deployed it to hundreds of nodes. And now I'd like to take a moment to go over some metrics in production with you from beacon. Now what we're looking at here is database latency in production. And what you're seeing is that we have a latency buffer time of 120 seconds plus the real-time latency, if you see there in the white box that I have marked. So for example, balances has a real-time latency of 6 seconds, creating a total latency of 126 seconds. Now, to kind of bring this full circle for you, to kind of really put the bow on and help you really kind of understand this much better. Now, when you go and place a trade in one of our platforms, and that order is executed, and you go back and you look at your orders that have been completed, For the first 126 seconds, every time you go back and look at those orders to see what that order that is executed, it will pull that from a primary read-write database. Now, when that entry gets to the point where it is 127 seconds old, it will actually then direct that call to go to a read-only replicant. And that's how we're able to handle that balance. Now here we're looking at beacon routing of a service over a period of 24 hours. If you see there in the first line that I have in the white box, we have 20.3 million calls, and those were handled by the beacon service. Now, of those 20.3, it had to direct 17.8 million to the read-only replicants and roughly 2.5 million to the primary read-write databases. Now, if you look on in the second white box I have marked here, this first line, what it's showing you is the response time from the beacon service when it came to routing a call. And it took 2.6 milliseconds for it to take and make a determination where that call needed to be routed. Now, on the second line, you have the primary read-only databases, and it took 12.2 milliseconds for those to respond when the call was directed to it. And in the last line, you have 21.8 milliseconds for the primary read-write database to respond. Now, you might be asking yourself, why did the primary read-write database take a little bit longer? Well, the primary database is taking in an immense amount of information that is being written to it. So as a result of that immense amount of information being written, it takes just a little bit longer for it to respond. Whereas your read-only replicants are only having the information copied to it. And so it's able to respond much more quickly and efficiently. Here we're looking at market open beacon service routing. And you can see here that Beacon handled 2.6 million calls in total, and 2 million calls being directed to the read-only replicants, and 647,000 only having to go to the primary read-write databases. Now here we're able to have roughly a little over 3/4 of our traffic going to our read-only replicants, which is incredibly efficient. As you might know, when market is opening, you have a lot of traffic that is taking place. You have a lot of orders being placed that are being executed. You have a lot of trades, everything. People are logging onto the platforms. So to be able to have this kind of load shedding is quite nice. And here we are looking at market close over a period of 1 hour. And here we have 580,000 calls being handled by the Beacon service. And of that, 562,000 were directed to the read-only replicants, and only 17,000 had to be directed to the primary read-write databases. Now, I'd like to take a moment and shift gears here away from Beacon. And share with you some things about Morgan Stanley. You've probably heard about our expertise in market analysis, wealth management, research, and market making. But there are a lot of other great things happening here. We have more than 75,000 people working in 41 countries. We have in-house startup accelerator providing financial and technical support to underrepresented entrepreneurs. We offer large-scale sustainable investing initiatives. And we have Girls Who Code summer immersion programs. We also have EMEA tech apprenticeships. And we have collaboration within small squads, enabling collective decision-making and innovation. I'd like to take a moment to recognize Huajun here, who's been presenting our architecture slides. He's actually the creator of Beacon. This was his vision, and it has been my pleasure to work with him as we created Beacon 2.0, brought that to production, and to work with him throughout this entire project. Oh, thank you.
It's a pleasure working with you. Yes.
Thank you, Huajun.